Hello?
Hi,
Professor.
Jubin.
Hi. Welcome.
Hi. Thank you.
And I made you a co-host so you can test and share the screen directly. Welcome. Thank you very much for making this seminar possible and giving a talk at the Harvard CMSA. Thank you very much.
Thank you.
You can also test your camera.
Oh, yeah. Oh. Oh, this. Yeah.
Yes, you should go direct to share, and then you will interrupt this. But please just go ahead, go direct to share. Yes, 直接分享，谢谢。
I just share my screen. Okay. Can you see my screen?
Yes. That looks great. You can share.
Share. Okay. Can you see the screen now?
We can, yes, and also this cursor, yes.
Okay, good.
We shall wait probably 2 to 3 minutes before we start, and I will introduce you. Thank you very much.
Okay, good. Yes.
Early
in Beijing.
Yeah. It's 8 o'clock.
8 a.m. Yeah, 8 o'clock.
Yeah, in the China time zone. I think 9 a.m. in Masaki Professor Oshikawa's time.
Yes. That's 9.
Hi.
And also, I think Australian people are not sure whether there's any, but the European people might be hard. But the West Coast and East Coast are possible.
So life in the US is close to normal, right?
I think so.
Great.
You mean pandemic? You mean the pandemic?
Yeah. Do you go to office now regularly?
Not yet. I think the office hasn't been open, but it will be open soon in August, mid-August. Yeah, I haven't been to my office for more than 1 year.
Yeah, it would be great to go back to normal.
That's why I feel like it's good to have a seminar, because that's the only way I can have a social. That's why I keep coming, because I feel like I need to talk to people otherwise. Well, many people have a family, but not me, not yet.
Yeah.
Sometimes I talk to people on the street. That's not a problem for me. Yes. Okay, so I think we may gradually start.
Yes.
I just respond to Mihail, but I don't know where he led me. I mean, I'm saying everything genuine and honest. In case I'm not making a joke, that's the reality. Okay, welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics seminar series. Today we are really honored to have a Professor Hong Yao Yao Hong speaking to us, giving this seminar. Especially, I really thank him to summarize some of his past work. As you'll see, the topic is on the title. I should also mention first that Professor Hong Yao has done a wide range of interesting work on this strong correlated electronic systems and condensed matter systems, and he did his PhD with Professor Stephen Chiverson at Stanford University, and later he went to UC Berkeley and Stanford University to did his postdoc under supervision of Donghai Li Donghai and Shouchen Zhang Shouchen. And currently he is a professor at the Tsinghua University Institute for Advanced Study, Tsinghua Dashi Gaoling研究院. Today, as I say, today is very honored speaking, summarizing his previous work. I feel there is still some room to develop these topics, and it's really nice to have the most suitable, one of the suitable pioneer on this direction, Professor Hong Yao, to summarize this work on direction on this emergence, spacetime supersymmetry in topological phase of quantum matter. And before we begin, I want to encourage the audience, please feel free to interrupt and ask questions. And when you feel appropriate, you can either raise your hands direct, or you can just ask appropriately. If you find time, you can ask directly if you find appropriate time. All right, thank you. So please take over. Yeah, thank you.
All right. First, I'd like to thank Juvin and other organizers of this seminar for the kind invitation. It's really my great pleasure to talk about my work about emergent space-time supersymmetry in topological phase of matters. Before I go to the content of this talk, I would like to thank my collaborators, my student Soke Jian, currently now at University of Maryland, Zhiqiang Li, formerly postdoc at Berkeley, just moved to IOP in Beijing a month ago. Yifan Jiang also moved to back to China in Shanghai Tech a few months ago. Joseph Macherko at the University of Albert, Chen Huanglin, University of Albert, Abu Hassan was a postdoc at Stanford. Now I think a faculty at in Iran, and Chris Mendel in TU Dresden. So I will base these papers to discuss my talk. The first two work is about the RG study of emergent SUSY. The second, this two work is about the Monte Carlo study of emergent SUSY in topological phase of matter. I believe that all of us are quite familiar with quantum critical point and emergent phenomenon. A quantum critical point is a continuous phase transition at 0 temperature by tuning some parameter in the Hamiltonian, such as pressure or magnetic field. At a quantum critical point, correlation lengths diverges, and many microscopic details are not essential to energy physics. Universality class emerge at quantum critical point. A remarkable feature at quantum critical point is the open emergence of larger symmetry. For instance, when the chemical potential of graphene is tuned to charge neutrality, the system at low energy has emergent Lorentz symmetry. At the deconfined quantum critical point between antiparallelic phase and when it's on solid phase, there's a believed emergence of SO5 symmetry. All these usual emergent symmetries, such as Lorentz symmetry and SO5 symmetry, are bosonic symmetries. Namely, the statistical of the particle doesn't change under this symmetry transformation. The main question in my talk I would like to ask is, can fermionic spacetime supersymmetry emerge at quantum critical point, or QCP, in condensed matter systems? Here's the outline of this talk. First, I will give you some brief introduction to spacetime supersymmetry, or SUSY. And I believe that many of you are quite familiar or even expert in this topic. I just give some brief introduction for those who may not be familiar with this topic. And also emergence of SUSY in condensed matter systems. After that, I will discuss renormalization group study of emergent 3+1 dimensional SUSY in the bulk of a 3-dimensional Weyl semimetal with 2 Weyl point. And then I will discuss more recent numerical simulation of microscopic lattice model to show evidence of emergent supersymmetry. For instance, we showed emergent 1+1 dimensional SUSY on the edge of a 2-dimensional topological superconductor, when the edge of 2-dimensional superconductor undergoes some tiny boson symmetry breaking. At this tiny boson symmetry breaking quantum critical point, we show there is an emergent 1+1 dimensional SUSY. And then I will discuss a quantum Monte Carlo study, the same problem-free quantum Monte Carlo study of emergent 2+1 SUSY on the surface of 3-dimensional topological insulate. The surface of 3-dimensional topological insulate has a single Dirac cone. At the superconducting quantum critical point of this single Dirac cone surface state, our numerical study shows that there is an emergent 2+1D SUSY. In the end, I will summarize and also mention some open questions. As I mentioned earlier, and usual symmetries are bosonic symmetries, namely the symmetry transformation are bosonic. For instance, the spin rotational symmetry, the symmetry generate just the spin operators, the SO3 spin operators, and translation symmetry just implemented by the momentum operator. And all these symmetries are bosonic symmetry in the sense that the statistical particle does not change under the symmetry. transformation. For instance, the fermion is still fermion, and boson is still boson after the symmetry transformation. However, SUSY is a fermionic symmetry, namely symmetry generates fermionic operators. The statistical particle also change under symmetry transformation. SUSY transformation, a fermion is converted to a boson and vice versa. Since each particle, the statistical particle changes under the supersymmetric transformation. So in a supersymmetric theory, each particle has a corresponding superparticle. For instance, electron is a fermion. In a supersymmetric theory, there's a corresponding superparticle called S electron, which is a boson. Photon is a gauge boson. In a supersymmetric gauge theory, it also has a corresponding superparticle called photon. So this SUSY, spacetime SUSY, was proposed more than 4 decades ago. Here is a more mathematical description of spacetime SUSY. So we have this SUSY generates Q alpha and satisfy this commutation relation. From this commutation relation, from this algebra, we can see that this supersymmetric generate or SUSY is kind of a square root of spacetime translation symmetry. Since this is an anti-commutator Q alpha, Q beta, which is equal to the energy momentum vector P mu. So it's like a take square root of energy momentum P mu, we get supersymmetry. And there's here I'd like to mention a very simple example of a supersymmetric theory, namely a free fermion, direct fermion mode plus a free boson mode with equal mass and equal velocity. So this part describes a free direct fermion with a velocity v and mass m. If we have also a boson with velocity v and mass m, and this simple theory is supersymmetric in the sense that it is invariant under this fermionic supersymmetric transformation. Here, this psi fermion is transformed into a boson. Phi is a boson, and this supersymmetric transformation is parameterized by this Grassmann parameter, not real parameter. Here is a supersymmetric charge or supercharge. So here I'd like to mention some hallmark of a supersymmetric theory. As I mentioned earlier, in a supersymmetric theory, each particle or each mode has a corresponding superparticle. So the number of fermionic mode has to be identical to the number of bosonic mode in a supersymmetric theory. The theory is usually a Lorentz invariant, namely there is only one velocity in the system. The velocity of boson has to be identical to the velocity of fermion. So there's one speed of light or one velocity in the low energy theory. Moreover, the boson mode and fermion mode have identical masses and other quantum numbers except the statistics. Boson and fermion have different statistics, but they have other identical quantum numbers. This is a last show of supersymmetric theory. So why is SUSY interesting and important? SUSY was introduced mainly attempting to solve fundamental issues in particle physics. For instance, solve the hierarchy problem, why the Higgs boson mass is so small. And also this grand unification, the gauge coupling flow to the same constant at high energy. Theoretically, SUSY helps to obtain many interesting and exact result in quantum field theory, providing deep insight into the quantum field theory. But evidence of SUSY in particle physics is still lacking. So far, the HC experiments are elective in finding evidence of a supersymmetric particle. So the question I would like to ask is, can SUSY emerge in quantum many-body systems in low energy and long distance, even though the microscopic lattice model are not supersymmetric? Actually, there are already many interesting and important theoretical proposals of emergent SUSY beyond high energy physics or in condensed matter physics. For instance, from the renormalization analysis, it was shown by Tyrone, Donation, and Ashwin-Vishwanas in 2014 that on the surface of a three-dimensional topological superconductor, if the surface of this 3D topological superconductor undergo a tiny boson symmetry breaking phase transition exactly at this tiny boson QCP, tiny boson breaking QCP, they showed that there is an emergent 2+1D SUSY at low energy and long distance. Moreover, just a few another interesting example is the emergent SUSY 1+1 SUSY on the edge of a Moritz non-abelian quantum Hall state, which was proposed by Professor Kun Yang and collaborator. They show that on the edge of a Moritz non-abelian fractional quantum Hall state, there is a fermion mode, and there's also a boson mode, chiral fermion mode and chiral boson mode. If the velocity of this chiral fermion is tuned to the velocity of the chiral boson by interaction or confining potential of this quantum Hall state, and this low energy effective theory of this edge of this Moritz edge state has space-time SUSY. Chauvin and Collaborators proposed to realize 0+1D SUSY at the boundary of 1+1 SPT phase. And so if you have a tiny boson invariant topological superconductor protected by T² equal to +1, for instance, for a nu equal to 2, there are two Majorana modes which are protected by the tiny boson symmetry. And these two Majorana modes can realize this 0+1D SUSY or supersymmetric quantum mechanics. Very nice things about this realization is that there's no fine-tuning is needed in the parameter space. So it's stable. So actually, there are many other proposals of emergent SUSY in condensed matter systems. So in this talk, I won't go into every works listed here. There are even many other works not listed here. The main question I would like to ask about emergent SUSY in condensed matter physics, in condensed matter systems, are the following three questions. The first question is, in all these theoretical proposals of emergent SUSY in condensed matter systems, they always below 3+1 dimension. So either 2+1 dimension or 1+1 dimension or 0+1 dimension. The first question I would like to ask is, can 3+1 dimensional SUSY emerge in the bulk of a 3-dimensional condensed matter system? So the answer is yes. We show that from the renormalization group analysis, SUSY can emerge at the superconducting transition in the bulk of a 3-dimensional Weyl semimetal. The second question is, can emergent SUSY be observed? Evidence of emergent SUSY be observed in unbiased and numerical exact or numerical simulation, such as sign problem-free quantum Monte Carlo? The answer is also yes. We observe evidence of emergent 1+1 SUSY and 2+1 SUSY in microscopic lattice model tuned at quantum critical point. The third question I would like to ask is, can SUSY with gauge field such as supersymmetric QED emerge in condensed matter systems? The answer is also yes. We showed that the supersymmetric QED may emerge on the surface of a topological insulator such as SMB6. The surface, if the surface has a 3 Dirac cone, which is protected by the C3 symmetry, instead of a single Dirac cone, if we have a 3 Dirac cone on the 111 surface of a topological insulator such as SMB6, we showed from RG analysis that supersymmetric QED might emerge on that surface.
Sorry, can I ask a question?
Yes.
So in the previous slide, you mentioned that there's a emergent
Yes.
SUSY and FQH state. Can you, because I understand the chiral boson and on the edge state sort of carries the charge polarization that characterize the quantum Hall invariant. Can you say something like, what's the physical meaning of the superpartner, that fermion, the chiral fermion?
The fermions are so the bosons carry charge. The fermions actually are neutral. So so this Morrid state has a non-abelian particle, quasi-particle in the bulk. So this is the H theory with both bosons and fermions, because the bulk is for this particular non-abelian state. So I'm not sure whether I correctly understood your question.
Yeah, I'm just asking about like a physical meaning for what this fermion is doing on the edge.
Physical meaning. So this is just this H theory, right? The H has a Majorana mode. Right. So this psi is a Majorana, the chiral Majorana mode.
Okay.
Or maybe Hank, you need to clarify what you asked him. I don't understand what you asked.
I'm sorry. Sorry.
I say Hank. Hank
Yep.
is the person who asked question. I said I don't understand what Hank is asking. Maybe Hank need to clarify the question.
Yeah, it's just that like in quantum Hall systems, usually we are able to understand like it's a Loniger liquid edge theory.
Yeah. This is a Loniger liquid. Yeah. Usually just chiral bosons, but this Morrid state has a fermion content.
Okay, maybe I'm just not very familiar with the.
Maybe let me rephrase. Are you trying to ask? Perhaps there's a fermionization and bosonization in 1+1D. So you may wonder what you separate fermion from boson. Why not just all bosonize the theory? Is that what you ask?
Yeah, that's one way to understand it.
And maybe I suppose the underlying fermion parity is still important. So I think you should separate the states to bosonic sector. Let's say some state you label by B, and there's some fermionic state labeled by F, and then the fermion parity exon boson is +1, fermion parity is -1, and these two sectors, I think should still be distinguished.
Yeah.
And even though you may be able to bosonize some fermion to chiral boson 1+1, chiral fermion can bosonize to chiral boson in 1+1, but if it's an abelian, suppose I go to abelian state, there's still this symmetric bilinear form for this K matrix still has odd integer, and that's the spin integral T in the bulk.
I see.
Yeah.
Bosonian fermion is still different.
I see. Okay. Thank you, Julian.
Yeah.
Can I ask a follow-up?
Yeah, you cannot.
Hey, Hong.
Yes. Hi, Chen.
It's Monte here.
Monte, yeah.
So For this 1 + 1 SUSY, this fermion is a chiral-Majorana fermion.
Yeah.
The chiral boson.
Yeah.
They have different central charge.
Yeah.
Right? So
Yeah.
I don't quite see like so with central charges that is completely observable. How can they be supersymmetric, or really naive?
The supersymmetric in the sense that, so if you do, I think I have a simple example here. So if you look at this theory, this is not chiral, just
right.
Non-chiral theory. So here, this theory just invariant on this transformation.
Yeah. I mean, yeah.
I'm not saying that you do the transformation, all the fermion just disappear going to boson. I just say that the theory has this symmetry.
I see. Okay.
Yeah. The central charge is different.
But that's fine. Like this is.
Yeah. That's fine. Yeah.
Okay. All right. Thanks.
Maybe I didn't get it. The central charge is different, but is the supersymmetry still works naively?
Yeah.
The coefficient different. So C is 1 and C is 1/2. Maybe I didn't get what you say. Sorry. The chiral boson is C = 1, and the other is the Majorana, chiral Majorana.
Yeah, the Majorana chiral C = 1/2.
So that's it's not your work, but maybe you already read the paper, so you can summarize why.
Yeah, this I think to be supersymmetric, there's no requirement of, I mean, the central charge to be identical. So I'm not saying that I'm not saying that after supersymmetric transformation, the fermion theory is totally converted to a boson theory. So you have a boson part, you have a fermion part. So after this supersymmetric transformation, and this theory just invariant, and this transformation is just a fermionic transformation, a fermionic symmetry. It doesn't mean a fermion is totally fermion disappear, totally converted to boson.
Okay.
There's no such symmetry.
Okay, but earlier you say some counting of a number of the fermions and number of boson degree freedom.
Yeah.
So they are part of the boson degree freedom may not be converted to fermion. There's only part of boson and part of fermion are converted to each other.
Yeah. So in order to be supersymmetric, the number of boson and fermion has to be identical. So since each particle has a corresponding superparticle, but it doesn't. I mean, the Lorentz theory doesn't convert it from a bosonic theory to a fermionic theory. It's not like the Jordan-Weyl transformation or fermionization. A boson theory is converted to fermion theory.
Okay, thanks.
I'm not sure. Yeah, that's answer your question.
Thanks.
So I may not get to question 3 because of the time, and
don't worry about the time. I think you should go to question 3 as well. Yeah.
Okay.
You can go.
And the first part I'd like to discuss is the RG analysis of the emergent 3+1D SUSY on the bulk, in the bulk of 3D wire semimetal. Probably many of you are quite familiar with wire semimetal. Let me say a few words about wire semimetal in kinetic metal systems. So wire semimetal, the Lattice model represent if there's 2 non-degenerate band touch at some discrete momentum point with linear dispersion. If you look at this energy dispersion, there are two. There's touching point 1 and touching point 2, and this is the simplest Weyl semi-metal in lattice model. And this is the low energy description of this Weyl semi-metal. This sigma x, sigma y, sigma z are just Pauli matrices, px, py, pz, just the momentum away from this Weyl point. In order to realize a three-dimensional Weyl point, the system has to break either tiny Bosons symmetry or Emergent symmetry. If both tiny Bosons and Emergent are respected, and the number of component has to be, the minimum number of component touching at a point has to be 4. That's the direct fermion. For the Weyl fermion, the system has to break either tiny boson or Emergent symmetry. A Weyl point is like the magnetic monopole in momentum space. So if you integrate the Berry curvature around the Weyl point, we get either plus 2 pi or minus 2 pi. It's like the magnetic monopole in momentum space. I just mentioned there's a fermion doubling theorem or no-go theorem, at least 2 Weyl point in a three-dimensional lattice model, namely the number of magnetic, the sum of magnetic charge or magnetic monopole has to vanish in the lattice model. So the minimum number of Weyl point in a lattice model is 2. The Weyl fermion or the touching point are protected by both translation symmetry and particle number conservation symmetry. If we allow to break translation symmetry or particle number conservation symmetry, the Weyl point can disappear. So in order to realize emergent SUSY, we consider a Weyl semi-metal with 2 Weyl points, which will be clear later. For instance, we assume there are 2 Weyl points at momentum plus k and minus k, and they are related by some symmetry, such that the energy of the 2 Weyl point are degenerate. So we can tune the chemical potential of the system to the energy of the Weyl point, such that the Fermi surface disappear. There's only 2 Weyl point at the chemical potential. So the 2 Weyl fermion mode, psi plus k and psi minus k, and for simplicity, I just call it psi plus minus. So to be possibly supersymmetric, and the low energy theory should also have 2 complex bosonic mode. I mentioned a number of times that in a supersymmetric theory, the number of fermionic mode has to be identical to the number of bosonic mode. So now we have 2 fermionic mode, one at plus k, one at minus k. So we would like to have 2 complex boson mode in the low energy theory. How to realize, so we have a fermionic system, how to realize 2 complex bosonic mode. So in condensed matter, one way to realize the complex boson mode is from the autoparameter fluctuation in a system with some broken symmetries. For instance, in order to have 2 complex boson mode, we would like to consider a phase, a symmetry breaking phase, which spontaneously break both gauge symmetry or particle number conservation symmetry and translation symmetry. So the gauge symmetry is a U1 symmetry. The translation symmetry is also U1 symmetry. If both symmetry are broken, we will have 2 U1 autoparameter. Namely, we will have 2 bosonic mode. How to realize a phase with spontaneously broken gauge symmetry and translation symmetry? A natural candidate is the pale density wave. A pale density wave is a superconducting phase with translation symmetry breaking, so that this pale density wave can provide a symmetry broken phase with 2 U1 autoparameter.
So this, sorry, just like a clarifying question. So
yeah, sure.
you're essentially considering FFLO, right?
Yeah.
I see. Okay, good. Thank you.
Yeah. A good point. So for a superconducting autoparameter, usually for the singlet pairing, we characterize this autoparameter by fermion pairing, and this represents the singlet pairing I sigma y. So in the spin space is anasymmetric, and this superconducting pairing amplitude has a form factor in the relative coordinate r minus r prime. There's also this capital R, that's the center mass coordinate. And usually for the BCS state, this delta of capital R is a constant. Namely, the Cooper pair has 0 momentum. The little f represent the internal form factor such as S wave, D wave, this symmetry factor. For the usual BCS pairing. So here I consider the finite momentum pairing, namely this center mass dependence is not a constant. So this the pairing amplitude has this dependence. So it has pairing at momentum plus Q and also pairing at momentum minus Q. And this pairing is called pair density wave or FFLO. And this is real. This pairing is real. And this pair density wave break both gauge symmetry and translation symmetry. You have two U1 autoparameter delta plus Q and delta minus Q. Like two superconducting condensate at momentum plus Q and momentum minus Q. So as I mentioned earlier, the mode counting is good. That's the first step for realizing a space-time SUSY, emergent space-time SUSY. Sorry. So we have two Weyl fermion and two bosonic mode from the autoparameter fluctuation. And this plus momentum Q is from the pairing psi plus psi plus, namely it's a intra-valley pairing. Okay, and this minus K pairing is from psi minus pairing. So it's also intra-valley pairing. So that gives you two complex autoparameter. The question is, can a pair density wave transition occur in Weyl semimetal? If such a pair density wave transition occur in Weyl semimetal, does SUSY emerge at the pair density wave transition? So we just consider a microscopic lattice model on a cubic lattice with two Weyl point.
Hong?
Yes.
Sorry for interrupting you.
Sure,
let me just make sure I follow the 2U1 order parameter. I think 2 slides earlier you mentioned there's this phase breaks spontaneously both gauge symmetry and translation symmetry.
Yeah.
And let me just make sure, how is that related to 2U1 order parameters?
Yeah, this is really a good point. Thank you for asking this. Here, so I have pairing plus Q and minus Q. It looks like you have two pairing condensate, but there's only one charge conservation symmetry, right? And these two condensate actually will couple at high order. So there are two ways to look at this problem. So one way is you have two condensate with plus Q and minus Q. And if you look at the high order composite order of this delta Q and delta minus Q, it has a CDW with momentum 2Q. So it breaks translation symmetry, and just two way to look at. You are absolutely right. There's only one charge conservation symmetry. There's only one gauge symmetry. So this condensate has a Josephson coupling.
Okay, let me ask again. So the gauge one is the particle number conservation, U1.
Yeah.
And translation usually is maybe a real R symmetry, and on the lattice should be Z. But somehow, do you regard translation as some kind of arma Z as U1? Earlier you said translation is U1. I just want to make sure I get it as U1.
So here I just consider some incommensurate translation. The momentum of this Q is incommensurate. So for incommensurate, so you can, it's like a sliding.
And that translation will be a U1 symmetry?
Yeah. So for instance, when you have a CDW or something break translation symmetry, you have cosine QR times plus a phase a factor phi, and this phi can be anything for incommensurate. So it's just like the U1 phase.
Okay. So then I have a 2U1.
Yeah.
Gauge particle hole, but gauge particle number conservation, and also the translation of a incommensurate or commensurate, sorry.
Incommensurate. Yeah, sorry, I should mention this. So for instance, if you have a translation by lattice constant, two lattice constant, that's not a U1 symmetry, right? Just Z2 symmetry. So here I just consider an incommensurate symmetry breaking in translation.
And then the breaking, and then there are 2U1, but somehow the 2U1 break down to some linear combination of 1U1. Is that what's going on? Or you break?
No, here you have 2U1. So the real symmetry in this model, symmetry breaking is one gauge symmetry and one translation symmetry. Both of them are U1.
And then what are spontaneous broken down?
The particle number symmetry is broken by the pairing.
And how about translation?
Translation is broken by the density weight.
So what's the initial global and what's the initial gauge, and what's the outcome global symmetry and gauge symmetry? Can you just say by the group, initial and final?
Yeah, so initial the gauge symmetry here just the particle number conservation. This psi to e to the I theta psi, just the U1 phase rotation in this fermion operator that represents the particle number conservation, and this translation. Originally, you have a lattice translation, and this you have. I mean, there are infinite number of translation operator, and if you have incommensurate CDW, so that's broken symmetry. It's like the U1 order parameter. The phase of this CDW can be any value.
Yes. I think you are explaining the condensed matter way. I'm trying to get just the equation or the most simple form. So I suppose there's a U1 global times U1 gauge, and I was asking what does it break down to? That's all. U1 global times U1 gauge break down to.
Yeah, just break totally break down to identity.
Oh, I see. Okay.
Yeah. Okay. Sorry. I mean, global the gauge. I mean, the fermion parity is still conserved. Break down to Z2. The pairing is still conserve fermion parity.
Okay, thanks. Thank you.
Yeah. And this is the lattice model we consider. This non-interaction part have two wire point, one at momentum. Both wire point are along the KZ axis. The Kx, Ky are equal to 0, and the momentum of the wire point is plus minus kz star, as I mentioned earlier. And this kz star is usually incommensurate. If I just consider this lattice dispersion, solve kz star, usually we'll get an incommensurate value from this lattice dispersion, from this dispersion. And we also consider an interaction in this model, namely just a simple Hubbard interaction, attractive Hubbard interaction, since we would like to have a superconducting transition. So we just consider the simplest attraction in this lattice model. Here I mentioned there are only 2 wire points from this non-interacting part. So this is a low energy description of this 2 wire point. So it has a Fermi velocity Vf and Vfx, Vfy, that's Fermi velocity in the xy plane, and also a Fermi velocity along the z direction. So the sigma is the spin indices plus minus, tau is a Weyl indices. So we have plus Weyl minus Weyl. Okay, just the simplest wire semimetal with 2 wire point, and also with attractive interaction. You can imagine this attractive interaction from some sort of electron phonon coupling. When you integrate out phonons, you get some retarded attractive interaction. Here, I just forget, just neglect the retardation, just considered as an effective instantaneous attraction, Hubbard U. And then this model is an interacting model, and we don't know how to solve that. And we first perform a mean field calculation to obtain a mean field quantum phase diagram of this model. This is a 3-dimensional model. We really don't have much numerical way to solve this model other than a mean field calculation. This model is sign problematic in quantum Monte Carlo. So we cannot solve it using quantum Monte Carlo. So we just do simple mean field calculation. So attractive interaction can induce 3 possible broken symmetries. The first just uniform pairing. Uniform pairing means the Cooper pair has 0 momentum. So we need to pair the fermions at plus k with fermion at minus k. It's called inter-valley pairing. However, this inter-valley pairing has node. It's a nodal gap. So this was articulated later in this paper by E. Lee and Duncan Holder, because the monopole charge in the pairing order pyramid is non-zero when you have inter-valley pairing. The second possibility is intra-valley pairing. This is what we want, the pair density wave pairing. The third possibility is since you have attractive interaction, charge density wave or CDW is also a possibility. Among these 3 possibilities, only pair density wave ordering can fully gap out the wire node. And so we expect that starting from the wire semimetal with attractive interaction, the first symmetry breaking phase out of this wire semimetal is a pair density wave. Indeed, from the mean field calculation, we found this phase diagram. The system initially is in the wire semimetal phase, and then there's a finite range of pair density wave. When the interaction is strong enough, each the spin up and spin down form a tightly bound pair, and then this pair form a CDW. Okay, but there is a finite range of pair density wave in the mean field phase diagram. Moreover, the transition from the wire semimetal to pair density wave is continuous. So now we have this mean field quantum phase diagram So have a wire metal which can undergo a superconducting transition into a pale density wave phase. And as I mentioned earlier, so we have two wire fermion, two fermionic mode, and also two complex U1 order parameter. And then we would like to ask, can spacetime SUSY emerge at this putative quantum critical point? To answer this question, we perform the renormalization group analysis of this pale density wave quantum critical point. So this is the low energy field theory describing this pale density wave transition. So this is the action has three parts. The fermionic part, and this is the bosonic part, like the Ginsburg-Nonor free energy part. And also there is a fermion boson coupling, the interaction between fermion and boson. The fermionic part is just the two wire fermions at value plus and value minus with velocity, three velocity, different velocity, Vx, Vy, and Vz. This is the bosonic part describe the pale density transition. And here, the boson also has three velocities, different anisotropic velocity, Vbx, Vby, and Vbz. R control this pale density wave transition. Nominally, when I equal to 0, that's the transition. The U is the interaction parameter. Here, I would like to mention that these two condensate has this interaction at the quadratic level. This 5 plus squared and 5 minus squared, they have interaction parameterized by U plus minus. So here I'd like to mention that this is related to Jovin's previous question. So the theory has only one particle number conservation theory. Why you have two superconducting order parameters? Actually, these two condensate can couple by Josephson coupling. However, when the momentum is incommensurate, the Josephson coupling actually is not allowed due to the translation, due to the momentum of this Josephson coupling is not equal to 0. So, for instance, if we look at this Josephson coupling, this charge 4e Josephson coupling, namely we have we hop two pairs from the plus condensate to the minus condensate, and this the momentum change in this process is 4k or the 4q, and since k is not commensurate, is incommensurate, so this has to vanish in this low energy effective theory, because the momentum of this term is not 0. When you integrate over the whole space, it has to vanish. So actually, this is important, and otherwise, the plus condensate and minus condensate they will couple, and the couple might be relevant or marginally relevant. Later, it will be clear that the vanishing of this charge 4e Josephson coupling is important for the emergence of this supersymmetry. I mentioned earlier the fermion velocity, boson velocity, and also the coupling of this for the quadratic term U, and G is this is the Yukawa coupling. Okay, and also U plus minus. And then for this low energy effective theory, we perform Argent analysis at dimension 4 minus epsilon. Eventually, since we are starting 3 plus 1 theory, so eventually we set epsilon equal to 0.
Excuse me.
Yes.
Question again. Just make sure I follow the setup.
Yes.
So you have a field theory at this stage,
Yeah.
but these are effective low energy field theory.
Yeah.
And earlier you have a lattice model. And how is the coupling that you study in the lattice model relate to the field theory that you study at the low energy? For example, in the lattice model, I think there are several hopping terms as T1, T2, T3, and TZ.
Yeah.
And also maybe some there's a PDW pairing terms.
Yeah.
Some notation of the U, big capital UG and the little u. I was wondering maybe you can comment about how this coupling are related to the field theory.
Yeah, that's a good point. So here, so imagine that you do some Hubbard-Sandwich transformation to get rid of this fermion coupling, and then when you do the Hubbard-Sandwich transformation, so you introduce two order parameter, two complex mode. Here the logic actually is different. Here I just assume there is a pale density wave transition, and this pale density wave transition is from the mean field calculation out of this Weyl semimetal, and then so we know there are two order parameters which describe the pale density wave transition. Usually, so this part is like the Ginsburg number of free energy of this symmetry breaking. However, since at low energy fermions are still gapless at 0 temperature, so we still need to consider fermion to describe the property of this quantum critical point. This velocity in the fermion part is related to the T1, T2, T3, TZ. Here, I just if I expand this dispersion, I think the velocity here is just lambda. So if I expand around kx equal to 0 and ky equal to 0, it will give you a fermion velocity lambda. And the velocity along the z direction, if you just expand this dz around kz star, kz star is some complex function of this T1, T2, and T3, and also TZ. And then you get the velocity. And the boson velocity is, yeah, I don't know how it relates to U. It's complicated. Just the phenomenological parameter in the low energy effective theory, assuming this pale density wave transition occur out of the YSM metal.
Is the capital U related to the small case U?
Yeah, it's related, and but it's not. It's a complicated relation.
Oh.
Yeah. So here, when you do the Hubbard-Sandwich transformation, and so you usually we just introduce a simple S wave order parameter, but here we need to introduce pale density order parameter at momentum k star, kz star. So there's a complicated relation between U, capital U, and small u, and also U plus minus.
The charge 4E Josephson coupling is not allowed. Can you also see from the latest that you forbidden certain terms?
Yeah, this so when we write down the Ginsburg number of free energy, write down the low energy effective theory, so all the terms has to respect the symmetry. So for instance, we need to check whether this term is charge 0 or not. So for instance, we cannot write a term with phi star, right? That's the carry charge 4E quantum number. So we need to write a term with phi star, phi star, phi pi. Moreover, and the momentum has to be zero in the low energy theory, namely it respect the translation symmetry. All the terms in the low energy theory has to respect the original symmetry of the model. So that's the reason this charge 4E is not allowed. If the Cooper pair has momentum, commensurate momentum, for instance, if Cooper pair has momentum plus minus pi over 2, for that case, and this charge 4E Josephson coupling is allowed. Because when you have two Cooper pair from minus condensate hop to the plus condensate, the momentum change is 2 pi. 2 pi is, in the lattice model, is equal to 0. That's just a reciprocal lattice vector. That's allowed if the Cooper pair momentum at plus minus pi over 2. However, for our model, the Cooper pair momentum is incommensurate. So this charge 4E Josephson coupling is not allowed by momentum conservation. Is that clear?
Thank you.
Right. And then we analyze the RG flow of this pyramid appear in this low energy effective theory. So we have the velocity ratio between the boson velocity and the fermion velocity, and we also have the velocity anisotropy, the velocity along the XY direction over the velocity along the Z direction. So this anisotropy called Wj, the velocity ratio between the boson and fermion is called Ag. And then this is the RG flow equation for this the velocity parameters. Sorry, there's some f which is some complicated function, and this is a RG. Just do the one loop RG, the standard one loop RG. This is the flow of this coupling constant, and this is the flow of G squared, the flow of U, and flow of U plus minus, and then we can solve this RG flow. First, we would like to see how the fermion velocity flow. Actually, this fermion velocity, the ratio between the fermion velocity, sorry, the velocity ratio actually flow to 1. That's the stable fixed point. Okay, so that's good, since we would like to have identical velocity between fermionic mode and bosonic mode. However, this anisotropy doesn't flow to 1. It's just there's the anisotropy just stays there at this fixed point. But that's fine. So the velocity along the Vx along the x direction can be different from the velocity along the z direction. Moreover, this coupling constant actually all flow to 0 when epsilon equal to 0 in 3+1 dimension. So the coupling constant originally is marginal. It turned out that this coupling constant is marginally irrelevant. It just flow to 0. However, they flow to 0. I didn't mention here in a special direction, namely the G squared over U actually flow to 1. So that's the supersymmetric condition. So here I'd like to mention that this U plus minus flow to 0. What is U plus minus? U plus minus is the coupling between the plus condensate and the minus condensate. And it turned out that at low energy, this plus condensate decouple with the minus condensate. You really have two independent superconducting condensate. So at the fixed point, so we will have two copies of this theory. Actually, this theory is very, very simple. So you have a copy of this free boson and a copy of this the Weyl fermion. They have identical velocity. This is true for the plus flavor and also for the minus flavor. So this theory is invariant under this supersymmetric transformation. And so we realize two copy of n equal to 2 spacetime SUSY. To the best of our knowledge, this is probably the first theoretical example of emergent SUSY in 3+1 condensed matter system. Although the fixed point theory is non-interacting in the sense that this all this interaction flow to zero under the RG. Sorry, is there any questions here?
Can I ask a question?
Sure.
Sorry, maybe I missed, but so in the phase diagram, you first presented, this is a SUSY critical point is supposed to be a critical point, phase transition point between the Weyl semimetal and PDW phase.
Yeah.
So where is the so you have relevant operator towards PDW direction? Maybe I missed.
I'm sorry.
In your RG flow, you said that this SUSY fixed point is stable. It has marginally relevant operator.
Yeah.
But there is also relevant operator which drives the SUSY fixed point to PDW phase, or
sorry, here we already set R equal to 0.
oh, okay.
Yeah,
so
just
R, if you introduce R, then that's
that's a relevant direction. Yeah.
Uh-huh.
Thank you. Yeah, that's good point.
Yeah, I see. Thank you.
So here I don't have slides here. Here we consider a theory, a Weyl semimetal with only 2 Weyl points. And how about 4 Weyl point or 6 Weyl point? How about more Weyl point? It turns out that if the theory has more than 2 Weyl point, for instance, 4 Weyl point, and then the reason is this Josephson coupling. So I don't have a plot here. So if you have a 4 Weyl point, and then you can have, for instance, you have this a couple pair, a pair from plus, a pair from minus, and then this can hop to, for instance, I label this 4 Weyl point as 1, 2, 3, 4, and 1 and 2 are plus minus momentum, plus minus k, for instance, and 3 and 4 are plus minus k prime. And when you have this 4 Weyl point and this the coupling, you hop a pair from 1 and 2 to the pair 3 and 4. This is allowed since that's the term has momentum 0, so it is allowed by the momentum conservation. And when that term is allowed under the RG flow, actually this will lock the phase. That term is actually marginally relevant. So that the different condensate, the phase will lock, so that the number of bosonic mode is less than the number of fermionic mode. Sorry, I thought I have a slide here. I don't have a slide here. So when you have more than 2 Weyl point, actually SUSY does not occur at the pale density wave transition. And I think in condensed matter or even in collaborator systems, there are now progress of realizing 2 Weyl point especially in collaborator systems. It was realized a few months ago by Professor Jianwei Pan group in USTC. And in cold atom, you can also implement attractive U. So hope that this kind of emergent SUSY might have some relevance in real system.
Excuse me.
Yes.
Is this 2 Weyl points versus 4 Weyl points that the 2 has the n equal to 2 SUSY, but not the n equal to when there's a 4 Weyl point, there is no. Is there some topological reason like a Ma2 Ma4 index, that type of things? As far as you know, maybe not.
Yeah, that's a good point. I don't know any topological reason. So here, when you only have 2 Weyl points, so you have 2 copy of this SUSY, and these 2 condensate, the phase does not lock. And when you have more than 2, you have locking. Any number more than 2, you will have phase locking between different superconducting condensate. So that's not good. When you have phase locking, namely some bosonic mode is lost in low energy.
Thank you.
Yeah, I don't know any topological reason. That's a good point to think about. Okay.
I have a question.
Yes.
Are there systems in lattice field theory in which there is emergent supersymmetry? You mentioned condensed matter.
Yeah.
But there's also lattice field theory.
Yeah. Yeah. So if you tune some parameter, I think you can realize. Here I would like to mention that I would like to start from a model which is not supersymmetric.
I mean, if you write down, for example, gauge field plus 1 adjoint fermion, either Wilson fermion or domain wall fermion.
Yeah.
Then for Wilson fermion, you have to do fine tuning to reach to the emergent supersymmetric point in the IR. But with domain wall fermion, or for example, of Kaplan, and in that case, UV theory is not supersymmetric at all. But the only relevant operator that can, that you can add is the fermion mass. But with domain wall, you can prevent that, and then in the IR, you are destined to have emergent supersymmetry.
I see. Yeah, that I am not aware of. Yeah, that will be interesting.
Maybe Miha can give a reference in the chat.
Yeah.
That would be great. Thank you.
Sure. I think there are more sophisticated examples as well. For example, at least in my opinion, this is a little bit philosophical point, but UVen always like, sort of unification rather than separation. So I think at least in lattice field theory, more or less all the examples of lattices which gives supersymmetry in the continuum have some sort of emergent supersymmetry. And the most sophisticated example of that is the formulation of N-equal for super Yang-Mills, which is a very special theory. Yeah.
You mean the supersymmetry on Mill
Yeah,
zero?
but I appreciate what you are doing. I mean, you are starting from, you know,
Lattice.
condensed matter, condensed matter system and getting SUSY. But if you think slightly more broadly, you know, starting with general lattice field theory with the right matter contents, you know, there are many cases in which we have emergent supersymmetry.
So although the lattice model is not supersymmetric.
Yeah, either that.
The continuum, when you take the continuum of that lattice model, it becomes
either that, or in the other example, for example, N=4 lattice model has only one exact supersymmetry. It squares to 0. It is not infinitesimal translation. So you can preserve just one exact supersymmetry on the lattice. And in the continuum, you have 16 supersymmetries. So in your language, one is supposed to say that, you know, 15 of the supersymmetries are emergent.
I see. Yeah, that's interesting.
But may I ask Miha, is that one, the SUSY is at the phase transition, or is just some IR theory of the?
It's IR theory.
It's
not.
It doesn't require phase transition. It doesn't require phase transition.
It doesn't require phase transition. So for the first example I mentioned with domain wall fermions, you have to. That case is you have to tune UV theory to weak coupling. Yeah, this is not. So in this sense, it is different from the description of the speaker. You know, in the speaker's description, it's living at the phase transition point.
Yeah.
If I may ask a question.
Yeah, sure.
You're probably gonna mention this later in your talk, but I was just wondering, are there any immediate, experimental observable consequences of particularly the supersymmetry, right? One can, of course, think about measuring some correlation function and the dimension would match between the boson sector and fermion sector. But do you have other comments on this experimental consequence of SUSY?
Yeah, actually, here I don't know for the pale density way. So the example I mentioned by Professor Kun Yang. So actually, he started this supersymmetric SUSY breaking, spontaneous breaking that give you the Agostino fermionic mode. So that's the prediction in the Morit edge state when you have edge constructions that spontaneously break the SUSY. There's some experimental consequences. The fermionic mode have quadratic dispersion, at least from their work. Yeah, as you mentioned, SUSY give you a lot of power to calculate correlation function. So you can, in some cases, you get exponent exactly. So that, I mean, if experimentally can measure those exponent, that's also the prediction of SUSY. Usually for high dimensional critical point, you don't have exact value for this critical exponent, but SUSY sometimes give you exact value.
I see. Thanks.
All right.
Sorry.
Yeah, please.
Sorry, there's one little thing that is kind of bothering me because there was also a mean field analysis of Weyl semimetals by Burkhoff, I think a few years ago. They studied like the competition between the BCS state and the FFLO state. They argued that BCS state is actually dominant, despite the fact that you have to have nodes. Yuri?
I don't know. I know there's a work by Joe Moore and a collaborator. They actually studied this wire semimetal, pairing in the wire semimetal when the chemical potential is slightly away from the wire point. Actually, they get the pale density weight.
I see, and that's a one loop calculation?
No, that's not I think that's the RPA or mean field.
Oh, okay.
Right, you have
Actually,
attractive interaction, you have Fermi surface, a tiny Fermi surface.
Right.
I think I read the work by Burkhoff on this comparative analysis. My recollection is that which one is leading instability probably depends on the detail of attractive interaction.
Yeah, it does. It does, yeah.
Yeah.
But he showed that there's a very small exponentially suppressed region where PDW can in fact be dominant, but yeah, it's just quite difficult, I guess, to
it certainly depends on the microscopic details. Actually, the node actually doesn't really give you much gain, right? Node just a point in the momentum space. Yeah, I mean that argument is not sufficiently strong to say that the PDW should always appear.
Yeah, that's true. That's true. Okay, thank you.
Yeah. All right. So now let me move on to the numerical study of emergent SUSY on the boundary or surface of topological phase matter. The first is the emergent 1+1 SUSY on the edge of a two-dimensional topological superconductor. Actually, this theory was proposed by this group of people, Tyrone, Donna, and Ashwin in 2014. So they suppose you have a two-dimensional topological superconductor, this with tiny Bosons symmetry. So the H theory are just helical majorana mode, just two component helical majorana fermion, real fermion. And then imagine the system undergo some tiny Bosons symmetry breaking on the edge. And then this tiny Bosons symmetry breaking will gap out this helical majorana mode. And this tiny Bosons symmetry breaking is an Ising type autoperimeter. The fluctuation give you a real boson. So they propose to have emergent SUSY at this tiny Boson breaking quantum critical point. So this is the low energy theory, and the RG will give you the emergent SUSY. And the question we would like to ask is, can quantum Monte Carlo verify the emergence of SUSY at this quantum critical point? So we just consider a model with P plus IP pairing for spin up electrons, but P minus IP pairing for spin down electrons, so that this H naught describe a tiny Boson invariant helical superconductor with a helical majorana mode on the edge. And then we, on top of this topological superconductor, we consider attractive U interaction. And this attractive U interaction will favor S-wave pairing. Okay, this is just a direct consequence of this on-site attraction. And we'd like to know what is the fate of this 2D topological superconductor under this strong Hubble interaction. So when the attraction is strong enough, as I mentioned, so we'd like to have a singlet pairing. And this singlet pairing actually break tiny Boson symmetry. Namely, we will have P plus IS wave pairing. The reason to break tiny Boson symmetry is to gain more energy. The bulk has larger gap, superconducting gap. Moreover, the tiny Boson symmetry breaking can also gap out the edge state. Okay, but for this tiny Boson symmetry breaking S-wave pairing, there are two possible quantum phase diagrams, two scenarios for the system with H. So the first scenario is that the bulk and H have the same quantum critical value of U at the tiny Boson symmetry breaking transition. The second scenario is that the H breaks the tiny Boson symmetry first, and then tiny Boson symmetry appear in the bulk of this two-dimensional system. The second scenario is more likely in the sense that In the original topological superconductor, the low energy physics happens on the edge, since the edge has helical Majorana mode. When you have interaction, the interaction will first have effect on the edge, low energy fermions. Eventually, the interaction will affect the bulk. But we need numerically unbiased method to test which scenario appear in the microscopic model. And yes.
Before you move on, may I ask a question about the previous,
Sure.
the two-phase transitions?
Yeah.
So in which sense is the second transition denoted as bulk QCP a separate phase transition? I mean, are there additional symmetry broken?
Yeah. So actually, the original model is already a superconducting model. So it's already subconductor. The symmetry breaking actually is a tiny bosons symmetry breaking. So you can imagine there's some mechanization, and the mechanization occur first on the boundary, and then at a different value, the mechanization occurs in the bulk. Since the edge has low energy fermion, right, it's gapless, but the bulk is gapped. So you can imagine
I would assume if the edge time result symmetry on the edge is broken, then, you know, by proximity effect or by coupling to the bulk, in the bulk, you would also have a similar time result symmetry breaking, right?
Yeah.
So this is why I'm asking about the second.
Yeah. So this the edge symmetry breaking, the order parameter decay exponentially into the bulk.
I see.
Yeah, it has some length scale into the bulk.
I see.
Yeah,
so it's not distinguished. They're not distinguished by different symmetry breaking, but the spatial profile of the correlation function.
Yeah. If you really calculate the bulk correlation function in this range of parameter, and then the bulk correlation is extrapolated to 0. So there's no bulk symmetry breaking in this range. So this is just a numerical detail. So I just we performed some Monte Carlo in the Majorana basis since this is a superconductor. So I won't go into the details of this numerical technique. So I mentioned earlier this order parameter is IASTU pairing, okay, which break tiny bosons symmetry, and we compute the Binder ratio. That's the standard technique to detect the phase transition. The Binder ratio of this order parameter. This is the second moment. This is fourth moment, and then when you get the ratio, you can when this ratio cross for different L, you get the critical value. So the difference between this figure and this figure is that, so this correlation is computed on the edge, only on the edge. And this correlation is computed in the full bulk. Okay. And from the edge, we get the critical value, which is less than the bulk critical value. So this numerical result clearly shows that there are two quantum critical points. The left one is the edge quantum critical point. The right one is a bulk quantum critical point. They are separate in U. Okay, this is the quantum phase diagram for a system with boundary. And this bulk quantum critical point, just the tiny bosons symmetry breaking, is the university class, just the 3D Ising transition. So we computed this correlation, critical exponent, and almost dimension. They're all consistent with the 3D Ising transition. But we are more interested in this edge quantum critical point, since we would like to see whether SUSY emerge at the edge quantum critical point. So we compute this the enormous dimension of this tiny boson operating order parameter on the edge. That's the bosonic enormous dimension. which is this value, and the correlation length exponent is this value. Since this critical exponent, sorry, this the critical exponent of this n equal to 1 SUSY, 1 plus 1 dimensional SUSY, the critical exponent are known exactly from the SUSY. This was known previously. The enormous dimension is 2/5. This correlation length exponent is 5 lines. So actually, the Monte Carlo result is reasonably close to the prediction of the theory. Moreover, SUSY, as I mentioned many times, it can change fermion and bosons so that the enormous dimension of fermion and boson, they have to be identical. They also have equal mass between fermionic mode and bosonic mode. So I computed this enormous dimension for the bosonic order pyramid. And also here I computed the enormous dimension of fermions. And it turned out that this enormous dimension of fermions is actually quite close to the enormous dimension of the bosons. So that's the manifestation of the space-time SUSY. So when we slightly move away from the quantum critical point, both fermion and boson acquire a mass. And we'd like to know how fermion mass and boson mass changes when we slightly move away from the critical point. It turned out that the fermion mass, so we can calculate the fermion mass and boson mass from the quantum Monte Carlo simulation. We found that the fermion mass and boson mass actually are equal around this quantum critical point. And so this is another manifestation of space-time SUSY, the equal mass between fermion and boson. Okay, so this is the summary of this quantum Monte Carlo study of this H quantum critical point and the emergent SUSY at the H quantum critical point. Okay, so I would like to here stop for a second to ask whether there are any questions for this part. Just a Monte Carlo study of this emergent SUSY.
Hi, Hong.
Yes.
Hi, a quick question. So how the boson mass and fermion mass changes we tune U away from the critical point seems to say that the SUSY is still valid even we are off critical.
Yeah, that's actually that's a good point. We actually SUSY emerged exactly only at the critical point.
Right.
But
those are
slightly away from the critical point, we want to ask how the fermion mass and boson mass scale with this U minus UC.
Yes.
Actually, the theory tells us that the scaling should be the same for the fermion and boson.
I suppose if there's an explicit SUSY breaking term, I could make behave. So it seems like there's no explicit SUSY breaking term being turned on, even though U is some microscopic parameter that.
Yeah, you're totally right. Away from the critical point, the theory is not supersymmetric. It's just approximately supersymmetric. So actually, if you look at the figure, the mass between fermion and boson, they start to deviate.
I see. Okay, that's
right. If you look at here,
right,
and so we think that they are equal in the leading.
Got it. I see your point. I see.
Yeah. Since they are SUSY breaking away from the critical point.
Mm-hmm.
Yeah. That's
okay.
Good
Thank you. Yeah.
All right. Now
I just want to mention, please take your time, so don't rush. And then if you want to take a coffee break or just a break, short break, we can also do that. But please.
I think I can continue.
Yeah, no problem. By the way, the numerics looks really, really great. It looks very nice to me. Yeah, thanks.
Thank you. Yeah. So now, let me move to the third part of this talk, the Monte Carlo study of the 2+1 SUSY on the surface direct cone of a topological insulate. So this theory was also proposed by Tyrone, Donna, and Ashwin, and also Sonsik in 2014. So here, a surface of three-dimensional topological insulate has a single direct cone. And imagine when the chemical potential is exactly at this direct point, and some interaction, imagine some interaction drives the system into the superconducting phase. Okay, by, I don't know, electron phonon coupling or proximity. So this there's a quantum critical point between this surface direct cone and the superconductor, surface superconductor. So at this critical point, they propose to have emergent SUSY, since this single direct fermion and this superconducting order parameter is a complex boson. This is complex fermion, and the boson is a complex boson. So this is the mode content is correct, and then the RG also tells you the fermion velocity and the boson velocity, they flow to the same velocity, and also the interaction have this special value at the fixed point. So the fixed point theory has an emergent SUSY, n equal to 2 emergent SUSY. Okay, so this is RG analysis is 4 minus epsilon, and this is different from my previous discussion on the Weyl semi-model. There, epsilon equal to 0. Here, epsilon equal to 1. So this is quite this interacting. So this at the fixed point, both U and G are non-zero. So we would like to ask, can this putative this 2+1D SUSY emerge at this superconducting quantum critical point? So there are two ways to simulate this problem. One direct way is just simulate a three-dimensional lattice model. But doing quantum Monte Carlo simulation with three-dimensional lattice model is computationally very cost. So instead we simulate a two-dimensional lattice model from quantum Monte Carlo. But there's again fermion doubling theorem. So the number of direct cones in a two-dimensional local lattice model with tiny Boston symmetry has to be even. So we would like to study a single direct cone on the 2D lattice. One way to do that is to use long-range hopping, namely, so we consider a hopping which is 1/r decay on the square lattice. So when you have this 1/r decay, when you do the Fourier transform, you get this perfect linear dispersion. Okay, actually this model respect tiny Boston symmetry, there is no violation of fermion doubling because of long-range hopping. Actually, this model was proposed in the 70s by a group of people at SLAC. So this kind of fermion is called SLAC fermion.
Hong,
yes.
So since in order to have a lattice model with a single direct cone, you already have to have a lot of long-range hopping terms. I was wondering whether it's possible to just do Monte Carlo in momentum space, because now on-site interaction will become non-local in K-space, but it looks like that's not really an additional price to pay, right? Because your lattice model already have long-range coupling.
Yeah, that's a good point. So I know there's there's a Monte Carlo study by in twist bilayer graphene they do QMC in Ashwin and Harrisburg. They in momentum space actually it can be sign problem free. Yeah, that's a good point. Yeah. So yeah, that might be good to look at that. Yeah, just do momentum space QMC. So here we actually this is a simplified expression for the hopping. The hopping is very complicated, but at long distance is 1/r decay. And this kind of slack fermion actually can capture many essential features of a single direction. For instance, if we have a domain wall on this lattice model, the plus mass and the minus mass. So along the domain wall, there should a chiral fermion. This is also observed by from the non-intact fermion, non-intact Hamiltonian, this Hamiltonian. So the next step is to realize a superconducting quantum critical point in this slack fermion. Again, we consider attractive U interaction for this slack fermion, and then this attractive U will, when U is strong enough, will generate on-site S-wave pairing, and then we would like to know the critical value of U where superconductivity occur. So this is the critical value of U from the quantum Monte Carlo simulation. When U is small, since the chemical potential is exactly at the direct point, so the weak interaction is irrelevant in the sense of RG, and you get a finite critical value of U, beyond which superconductivity appear. And then we compute various value of various critical exponent. For instance, this enormous dimension of bosons. So we just calculate the pair-pair correlation and then see how the pair-pair correlation decay as a function of distance. And the enormous dimension of fermions, just the fermion correlation, how it decays as a function of distance. The correlation is exponent nu. The correlation diverges with U minus UC. UC is the critical value for this superconductivity at 0 temperature. And this is a value we obtained from quantum Monte Carlo simulation. The enormous dimension bosons, enormous dimension fermions, and the correlation is exponent. And then we would like to compare the quantum Monte Carlo result with known theoretical result of 2+1D SUSY to see whether they are consistent or not. First, because of this 2+1 n = 2 SUSY has a special property, namely enormous dimension is known exactly because of the R symmetry. So the exact value is 1/3. So our numerical value is actually quite close to 1/3. Moreover, this correlation as exponent, actually there is no exact value for this 2+1 SUSY, but from the conformal bootstrap, the value is obtained for this n = 2, 2+1 SUSY. That's 0.917, which is also consistent with our quantum Monte Carlo simulation. So we think that our Monte Carlo simulation show strong evidence of emergent SUSY at this superconducting quantum critical point of a single direction. Although we didn't really simulate three-dimensional topological state with surface superconductivity, but from this two-dimensional lattice regularization of this single direction, we think although it has long-range hopping, we think the critical exponent is not affected by the long-range hopping, and our quantum Monte Carlo result are consistent with the SUSY prediction, the theory prediction. So that's a strong indication that SUSY emerged at this superconducting quantum critical point on the surface direction. So,
just make naive question about the numerics. It seems
yes,
here the data shows nicely the critical UC is independent of the system size choice, right? From the 13 to 21, for example, the first figure.
Yeah, actually, if you blow up, if you zoom in, you will see there is some shift of the crossing point.
Okay.
It's not perfect. I mean, so the data point is here and here. The crossing is in between. Yeah. Just this value, I should write. There should be some error bar. 0.83 is not exact value, just some approximate value from this numerical simulation. There should be an error bar here for this critical value of U.
I was just wondering, what are the roughly the system size that the data, the critical this coupling will converge?
Yeah, so
is there some number that just empirically I can get the size, just roughly understand the system size requirement?
So usually, so you see the crossing to see how the crossing changes with L, and if the crossing barely changes when L is large, for instance. So here we up to L equal to 21, and we can look at the crossing between 19 and 21, and the crossing between 17 and 19, and then we can compare these two crossings. If it doesn't change much, we think that's saturated. Yeah, there's always a criterion when you stop, because you need to stop somewhere. Moreover, L equal to 21 is kind of the largest system size we can access.
Okay.
So beyond that, computationally, we need a lot more time. Yeah.
Thanks.
I mean, ideally, we can. It would be great to calculate L equal to 100, but it's not practical. Then it will give us more accurate value of this critical exponent. I think it will be more and more close to this exact value. But I think up to this accuracy, we think it already provides strong evidence of emergent SUSY at this critical point. Eugene mentioned the experimental evidence if SUSY emerged at this quantum phase transition. Here I mentioned one interesting experimental consequence of SUSY. So actually this was proposed by William and Joseph in 2017. So at this superconducting quantum critical point of a single Dirac cone, they compute this this optical conductivity. This optical conductivity at 0 temperature, namely at this quantum critical point, the optical conductivity is a function of omega over t, because of this the CFT. So it only depends on the ratio of omega over t. When the temperature goes to 0, namely you compute sigma of infinity. And this quantity for supersymmetric surely can be computed exactly, although this is a 2 + 1D CFT. Well, this sigma of infinity, omega over t equal to infinity, can be computed exactly. And so this value is 0.226, approximately 0.226. And this is very different from the non-interacting Dirac point. So that only gives you a much smaller value. So I think this is a very important prediction of emergent SUSY at the superconducting quantum critical point. And other predictions, for instance, the density state, the exponent is changed by SUSY, and this exponent is known also exactly. This can be measured by STM. I think it's close to 2 hours. So let me summarize here. I discussed the three aspect of emergent SUSY. First is the RG study of 3+1 dimensional SUSY in the superconductor pale density wave transition critical point in 3D wire semimetal. And then I discussed the quantum Monte Carlo simulation of emergent 2+1D SUSY and 1+1 SUSY. So here I just want to mention some open questions. So we don't have numerical verification of a 3+1D SUSY yet in a microscopic model. Moreover, I mentioned the supersymmetric gauge theory. That's from the renormalization group calculation, but we do not have numerical observation so far of a supersymmetric gauge theory in microscopic lattice model. With that, let me thank you for attention.
Thank you very much. Thank you, Professor Hong Yao, for the wonderful
Thank you all.
seminar. And I believe that he will be willing to tell us more later about the emergent 3D SUSY QD. But let's pause for a moment to see whether the audience have any questions.
Yeah.
And please go ahead.
So can I ask a question?
Sure.
So yeah, going back to the first part, so you showed a phase diagram that if you crank up U, then system enters the CDW phase or something.
Yeah.
CDW, and that critical point. So you don't expect SUSY there in this UC prime.
You mean between PDW and CDW?
Yeah. So
No.
Is the nature of this
gapped.
Oh, okay.
So this is just something like some bosonic transition.
I see. Okay, I see.
Yeah, this CDW actually the CDW of pale. I mean, this is also CDW of pale density wave, but one is the superconducting phase. This is the insulating phase. Because this actually the momentum is changed to pi, because this is really a tightly bound pair, and this tightly bound pair in the second order process will have some repulsion, such that one sublattice is occupied by the pair, the other sublattice is empty. Yeah. So yeah, this is the mean field phase diagram. I mean, moreover, U is large. The critical U is comparable to the bandwidth. So it's not guaranteed, as previously discussed, it's not guaranteed PDW appeal. Sometimes maybe uniform pairing can appeal. It really depends on microscopic detail.
Good.
But here we just want to show that if such pale density wave transition occur, SUSY should appear at this transition.
So
looking at
please.
Sorry, Masaki, you were about to say something else.
Well, I just wanted to ask. So maybe I missed, but in the latter part of your talk, you introduced quantum Monte Carlo simulation for lower dimension models. But this 3+1D, is it difficult to do quantum Monte Carlo? By some essential reason, or just a computationally more challenging because of the higher dimension?
Yeah, I think I think the reason is certainly computationally it's more challenging, but I think more importantly, we need a sign problem-free model, which can feature this kind of transition. So I discussed the two models. So we just purposely design such a model, which is sign problem-free. But for this 3+1D case, the Weyl semimetal to the pale density wave transition, we currently don't have a sign problem-free model. Yeah. For instance, if we have a sign problem-free model for the two-dimensional lattice, we can calculate like 1,000 lattice site, and then that's if you take a cubic root, that's 10. So if we have a three-dimensional lattice model, which is sign problem-free, and at least we can compute up to L equal to 10. But currently, we don't have a sign problem-free model with the pale density wave transition.
I see. Thank you.
Actually, we don't have any sign problem-free model, even in two-dimensional. So the pale density wave, there is no controlled realization of pale density wave, even in 2+1 dimension.
I see.
So we did for some special model, we did DMRG study to show some evidence, but I think in terms of current cubic development, a pale density wave model is actually desired.
I see. Yeah, thank you.
Then next should be Yuquan.
Yeah, Yuquan knows a lot about pale density wave.
Excellent. All right. Yeah, thanks. So I'm trying to get a better idea of what's the necessary ingredient to get SUSY. Let's take this system, the Weyl system you're currently showing.
Yeah.
So suppose I have another kind of interaction that features, a phase transition between a uniform superconductivity and a pale density wave state. Then in that case, we know the uniform superconducting state, it does have point nodes. So these are basically the Weyl nodes of the Bogoliubov quasiparticle.
Yeah.
Right? So yeah, if I do a simple counting, it looks also very similar, right? You have a bunch of linear dispersion fermionic quasiparticles interact and the bosonic order parameter that becomes gapless at the transition point. Should I expect to also have emergent SUSY in this setup?
Yeah, I think that's very interesting. I thought about it. So when you have two Majorana wire, right? Here it's a real the complex wire.
Yeah.
You have two Majorana wire point in a superconductor, and then you have some CDW transition. I think in terms of mode counting, that's correct. I think there's a large chance. I think the mode counting is the first step. So you want to, the theory at low energy has identical number of fermionic mode and bosonic mode.
Right.
Once this is realized, I think there is a large chance that SUSY can emerge.
I see.
Yeah.
I would say one possible benefit of a setup I just mentioned would be, in that case, you can actually have a chemical potential. You can initially start with a Fermi surface. Right. Yeah. Okay.
Yeah. That's a good point. Here, I think this proposal by Ashwin, so on the superconductor of this surface state of 3D superconductor. So that's already a superconductor, right? You have the surface Majorana cone, and here you don't need to tune the chemical potential. You only need to tune the interaction of some other parameter to break the tiny boson symmetry on the surface to get the emergent SUSY. The example I mentioned, this Weyl semimetal, actually, you need to tune two parameters. The first is the chemical potential, right? You lead the system at the chemical potential, or the material is stoichiometric, such that the chemical potential is at the Weyl point at half inning. And then you tune some interaction. Yeah, for the superconductor case, you don't need to tune the chemical potential. That's a plus. Yeah, that's a good point.
Thank you.
Next will be Chenmeng.
Okay, so question is, are there examples of like emergent SUSY that is not just free fermion plus free boson, like the interacting theory in low dimensions? I know like n equals 4 young supersymmetry young Mills is interacting, but like in lower dimensions, do you know anything like this?
Yeah, this 2 + 1 actually are interacting.
Okay, I see, right, yes.
Yeah, only the 3 + 1 are non-interacting.
Right, yes.
It will be interesting to have an interacting 3 + 1, so
well,
both 1 + 1 and 2 + 1 are intact.
That's right, yeah, 1 + 1, the tricritical icing, and 2 + 1.
Yeah.
Okay, sorry. Maybe another comment that you mentioned that there's no controlled realization of pair density wave.
Yeah.
But I remember that I learned this example from you and also Sun Kai, that if you have 2 quadratic band touching at different momentum, then you can get a pair density wave at infinitesimal interaction between the 2 barrier density waves, between the 2 quadratic band touching points.
Yeah, so there.
Does that count?
So if you have a quadratic band touching point at +k and -k, and since in 2 dimensions this the density of state is constant, indeed this mean field is reliable, or RG is reliable, since you have weak interaction. Yeah, I don't know. So I think we don't have pair density wave there. So there's a possibility that some interaction will drive the system into the intra-valley pairing.
I thought intro-valley is not possible, right? Because it's a quadratic band touching. So if you just look at one quadratic band touching, the attractive interaction is marginally irrelevant.
Yeah.
So you don't have inter. So you only have inter-valley pairing.
Yeah.
And
Inter-valley will give you 0 momentum.
Yeah, if you design a model so that the 2 band touching points are at different momentum, 0 pi.
Oh yeah. And then if 2 different momentum, it's hard to tune their energy to be identical.
That's true. Yeah.
Right. When you tune the energy to be identical, and then it's possible to have inter-valley pairing such that the momentum is finite.
That's right. Yes.
Yeah, that's good.
But it requires a little bit of fine tuning, maybe.
Yeah.
Or maybe some global symmetry.
Yeah. Maybe some global symmetry will be great.
Okay. All right. Thanks.
So if no more question, maybe we can have Professor Hongyao to continue to discuss the emergent SUSY QED and the nematic PDW critical point that have.
Yeah, sorry to keep you.
We want to hear. We are here to hear. We are here to listen to your story. Thank you.
So let me. sorry, I think I put it here. Yeah. So we'd like to have some emergent SUSY with gauge field. So previous example we discussed have no gauge field, and so the model we started is the surface state of a three-dimensional topological insulate with 3 direct cones. So imagine SMB6 is a strong topological insulate. On the 111 surface of this strong topological insulate, it has 3 direct cones. And at the 3 inequivalent endpoint, these 3 points are related by symmetry, so that the chemical potential can be tuned to these 3 direct points. Okay, and then we consider some possible pairing, the inter-valley pairing, as discussed with Meng. So when you have inter-valley pairing, the total momentum can be non-zero. It's also pair density way. For instance, we pair psi 1 with psi 2, and psi 2 with psi 3, and psi 3 with psi 1. So we have 3 possible inter-valley pairing. The corresponding order parameter is called phi 1, phi 2, and phi 3. Okay. I mean, we don't know any microscopic interaction. Just imagine you have such inter-valley pairing. And then there are first the symmetries. So we analyze the symmetries on the question. So this system has the U1 symmetry or particle number conservation symmetry. But pair density will break. The system, the surface state also, the surface also has a C3 rotational symmetry. So limiticity can also break the C3 rotational symmetry. C3 rotational symmetry in the low energy sense is identical to U1. So for this pair density wave, there are 2 possible pair density wave. One is the isotropic pair density wave. Namely, the phi 1 order parameter is equal to phi 2 and equal to phi 3. But this is what we want. This preserves C3 rotational symmetry, only break the U1 symmetry. And we want the system have more symmetry breaking in the sense that the system can have more chance to be supersymmetric. So we consider the lemmatic pair density wave, namely only one order parameter is non-zero, the other 2 are 0. And this order parameter breaks the C3 rotational symmetry, also breaks the particle number conservation symmetry. And then we study the low energy effective theory of this lemmatic pair density wave transition. Okay, and so this is the fermionic part. You have 3 direct fermion, complex direct fermion, 2 component direct fermions. And this is the bosonic part. You have 3 order parameter, phi 1 and phi 2 and phi 3. And so this U is the coupling between 1 and 2, 2 and 3, 3 and 1. And U prime is like the Josephson. So now this is the charge for E, Josephson coupling, right? So when you have a 2 couple pair in the phi 1 condensate can hop to phi 2, right? So because the momentum is at M point, so the 2 couple pair momentum is identical to 0. So this charge for E is allowed. So you have U prime. The U double prime is the usual phi force term. And then you have this the Yukawa coupling, the boson fermion coupling. So in order to get the lemmatic pair density wave, so we need some condition. And this theory describes both isotropic pale density wave and nematic pale density wave. To have nematic pale density wave, so this U plus 2U prime minus 2U double prime, just look at the potential of these interactions between different condensate. So this is a condition for nematic pale density wave, just to favor one condensate, the other two are 0. And then we do RG analysis of this nematic pale density wave, namely set I equal to 0. Just look at the quantum critical point. Is there any questions up to this point, this setting? Yeah, if not, I will move on. So again, the RG calculation, again, here you have many parameters, the velocity, this coupling, and then the RG calculation actually give rise to some stable fixed point. The fermion velocity, again, identical to the boson velocity. Moreover, this is 2 plus 1 theory, the U equal to G squared. That's good for usual Western supersymmetric theory. Moreover, this U prime and U double prime, they flow to 0. Actually, this is a tri-critical point. So if you look at this phase diagram, and so this tri-critical point separate the second order phase transition from the first order phase transition. Okay, and only this critical point is a stable fixed point. So this is the tri-critical point. Moreover, and this tri-critical point at this value, stable fixed point value, has supersymmetric property, namely the supersymmetric XYZ model. So if we do this SUSY transformation, this theory at this fixed point is invariant. So the low energy theory is a supersymmetric XY model. So it has 3 direct fermions and 3 complex bosons. They are supersymmetric partners of each other. And up to this point, there is no gauge theory. It turns out that this supersymmetric XYZ model is due to this supersymmetric QED by mirror symmetry. It's like the fermionic version of this particle vortex duality. And this was known many years ago. So this 2 plus 1D SUSY XY is due to the 2 plus 1D SUSY QED. In this sense, we think that we realize a supersymmetric gauge theory in condensed matter systems. So that's the story for this supersymmetric gauge theory. Yeah, that's what
sorry,
I want to share.
If I may ask about the previous slide.
Yes.
So you mentioned there are 3 bosonic fields, right? But
yeah.
As I see from the phase diagram, it's entering a nematic PDW, right?
Yeah.
So right, even though there are 3 gapless bosonic points right across the phase transition, only one of them condenses.
Yeah. So it's at this critical point, not in the phase. The phase only, at the critical point, the fluctuation of all 3 occur.
Right. I see.
Yeah. Although the phase is a nematic phase.
Yeah, this is interesting because upon on the other side of the phase transition toward isotropic PDW, there is also the endpoint of first order transition line, but there is no supersymmetry.
No.
I see. Okay. Is there an intuitive way to understand why to get SUSY you can only have one of the 3 boson condensed?
Yeah, so this intuitive understanding is this. So you want to break more symmetries. So you want to know how many underlying physical symmetry is broken. And if it's a limmatic phase, you break not only the particle number conservation, you also break the C3 rotational symmetry.
Right.
So that give you another U1, right? C3 in low energy is a complex order parameter.
Oh, I see. I see. So it sort of flows to an emergent U1.
Yeah.
I see.
So that's my intuitive understanding why a pneumatic pale density wave is works better than the isotropic pale density wave.
So are you saying it's like a pseudo Goldstone mode corresponding to the breaking of the C3 rotation? That's also one of the participants in supersymmetry?
No. So for the isotropic case, so you want to know whether this, although you can identify 3 Peonic order parameter 5.1, 5.2, 5.3, right? And so actually the physical symmetry only have 1 particle number conservation. So in the sense that, so if you want to, yeah, this. So if you look at this this charge 4E term, so this charge 4E might can flow to relevant,
right?
In the sense that, so although so you have 5.1, 5.2, 5.3, but the phase of this 3 condensate, they strongly locked.
I see.
Since you want some 3 complex boson mode, right? They can be superpartner of 3 complex fermions. But if this the complex boson mode, they already strongly locked. Namely, they are not. I mean, it's not good for SUSY.
I see. That makes sense.
Yeah. So this is so you really want to break more physical symmetry. Otherwise, when they lock, you have Laguerre mode, right?
Yeah.
It's the condensate, different condensate they couple. Yeah, that's my intuitive understanding.
So about this SUSY XYZ, is it again like a 3 Dirac plus 3 boson, or it's like
Yeah. 3 Dirac plus 3 bosons. So you have
interactions are forbidden by the supersymmetry.
I'm sorry.
Interactions are forbidden by the supersymmetry, or
oh, sorry, it's still intact model.
Okay.
So you still have this.
Oh, I see. But the value of U and G squared, there's no particular fixed point value.
No, so this can change. This there's no SUSY doesn't require a particular value, just the relation U and G squared identical, so that this theory is invariant under this supersymmetric transformation.
Do you mean that there's a line of fixed point, or there's?
Yeah. This I don't know whether it's a line. You still have other condition.
Yeah, sure, but it seems like the U, let's say the value of U is not constrained at all by the fixed point or by this calculation.
No. So the what's symmetrical SUSY, this U and G squared, they just equal.
Okay. So does it mean that, for example, the scaling dimensions and all these properties at a fixed point, do they depend on U?
No.
Okay.
It's like
So
the Wilson Fisher, right? The phi force. Yeah.
I see. So there is a fixed point with some.
Yeah.
And the fixed point is not a decoupled free Dirac plus free boson.
No.
Okay, I see.
No.
But do we know like the data of the fixed point? Like what's the dimension of operators?
Yeah, I think there is some critical exponent know exactly. I think the correlation as exponent.
I see.
Sorry, anomalous dimension, I think. Yeah, I think anomalous dimension is no.
Okay.
Yeah, I think this all in this paper, this Huajia Wang.
I see. Okay. Interesting.
Yeah. We don't really have a case theory, just map to a supersymmetric case theory.
Well, whether something is a gauge theory or not is sometimes ambiguous.
Yeah, that's true. Yeah, it would be good to really have a supersymmetric gauge theory emerge in the condensed matter system.
Right.
Maybe let me ask, if the internal symmetry of a lattice model somehow is also gauged instead of global symmetry, then will the critical point have a additional emergent gauge theory, like make the critical point also become emergent gauge theory? Can you foresee this possibility?
That's a good point. Yeah, I think in emergent SUSY, if you start with some gauge field, and it's not, I think it's challenging to realize this the superpartner of gauge bosons. Yeah, I don't know how to realize gauge fermion. So I think it's not straightforward to, if you really have a gauge boson gauge theory in the lattice model, and then I don't know how to. It will be very interesting to realize supersymmetric gauge theory starting from such models, but it's not clear to me how the gauge fermion can be realized. Can emerge in low energy. Yeah, it would be interesting to have such model, such realization.
Thank you very much.
Thank you.
Any more questions from audience? And I think it's about time, but that's great. Thank you.
Thank you. Yeah.
Sorry
to keep you late.
Yeah, no. I really appreciate it. It's wonderful. It's great. I'm very happy. Thank you.
Thank you.